Okay, welcome to section 4.1. What I'd ask you to do here is to read this section very carefully, and especially the definitions and properties in this section. And what I want to do in this video is kind of show you how they fit together. The first definition says a function has an absolute maximum at x equals c if f of c is greater than or equal to f of x for all x in the domain of f. And so it's important whenever you ask yourself if something's an absolute max, you have to look at the entire domain of the function. So look at this first example. This function, the domain, since it's not specified, we're going to have to infer that it's all real numbers. Do we have an absolute max or min here? The answer is yes. 9 is the absolute max because 9 is greater than or equal to all the other f of x's in the entire domain of f. And notice there's no absolute minimum. The second function, again, since there's no domain specified, we're going to have to assume it's all real numbers. Is there an absolute max or min in this for this function? The answer is no, because there is no y value that's greater than or equal to all the others, and there's no y value that's less than all the others. But look what happens if we restrict the domain. If we just look at x from -1 to 3, do you see the whole picture changes? Now the absolute maximum is for this function on this domain is 24, and the absolute minimum becomes -3/8. So don't get the absolute max or min confused with the local max or min. The local max or min, you're not looking at the entire domain. F of x has a local max at x equals c if f of c is greater than or equal to f of x for all x near c. And what that means is in an open interval around c on both sides, f of c has to be greater than all the other f of x's. So think of it like a turning point for basically is what it is. All right, so look at this function. We're looking at the function we looked at before. Notice, even though this is not a absolute max, we'd still call this a local max, because if you look on both sides of -1/2, you're looking at a piece of the graph, this does appear to be a max. So 3/8 is a local max, and using the same reasoning, -3/8 would be a local min. Square root of x, it turns out there is not a local min here, because remember, you have to be able to talk about an open interval on both sides at x equals 0, and since you can't define the function to the left, we wouldn't call it a local min. This is, however, an absolute minimum, isn't it? How about sin x? Well, we are going to have a local max at 1, which notice it reaches the local max infinitely many times. Local minimum is going to be -1, which it also obtains infinitely many times. By the way, those are also absolute max and min. Okay, an important theorem in this section is what's called the extreme value theorem. It says, if you know a function is continuous on a closed interval, a, b, then you are 100% sure that it will obtain both an absolute max and an absolute minimum somewhere on a, b. So if you look at this function here, this function is a polynomial that's continuous on -1 to 4. The theorem says it will definitely have an absolute maximum and an absolute minimum. Notice the absolute maximum occurs at the left endpoint, and it's 37, and the absolute minimum occurs at what's actually a local minimum. So the absolute minimum is -27. Let's look at some more. So the theorem says if a function is continuous on a closed interval, you know that it has to have a absolute max and min. Well, here we go. X squared is continuous on 0 to 1. The absolute maximum is 1. The absolute minimum is 0. But look at what happens if we just change it to an open interval. It turns out we would no longer call this an absolute maximum, because it has to actually obtain that value. And since there is no y value next to 1, even though the y values are getting close to 1, they never actually there is no y value that's greater than all the other ones. So this function, believe it or not, does not have an absolute max. And for the same reasoning, it doesn't have an absolute minimum on the open interval 0 to 1. What's wrong with this? Here we have a closed interval. The closed interval is -1 to 1, but notice again, this function, 1 over x, does not have an absolute max nor an absolute minimum on this closed interval. The answer? It's because the function is not continuous on the closed interval. So you see why you need those two things together. Okay, let's see a few more things here. We have an important theorem called Fermat's theorem. Fermat's theorem says that if you have a local, now we're talking about local max and min again. If you have a local max or min at x equals c, and if the derivative exists, then the derivative must be 0. We've already seen this before. I believe we were using this theorem when we were graphing the derivative function. f of x equals x squared has a local min at x equals 0, and the derivative is 0 there. But be careful, you could also have a local min, like absolute value of x, where the derivative is undefined. And most importantly, make sure you understand what Fermat's theorem does not say. It's possible to have a function where the derivative is 0, but not have a local max or min there. That does not contradict Fermat's theorem, because Fermat's theorem says the converse. If you have a local max or min, and if the derivative exists, then it's 0. But it's possible for the derivative to be 0, but not have a local max or min. Okay? We have a special name for values of x where the derivative is either 0 or undefined. Think of these values of x as candidates, places where you could possibly have a local max or min. They're called critical numbers. The important thing here is they have to be in the domain of the function. If x is in the domain of f and the derivative is 0 or undefined, we call that a critical number. How do you find the critical numbers? Well, for this function here, you take the derivative, set it equal to 0, solve for x. So plus or minus 1 over square root of 3 is a critical number. It's possible to have a critical number where the derivative is undefined. It doesn't happen that much, but it's possible. Take the derivative, set it equal to 0. Well, it's never equal to 0, but notice it's undefined when x equals 0. And f of 0 exists, so 0 is in the domain of f, so therefore it's a critical number at x equals 0. Be careful though. If you take f of x equals 5 over x minus 2, you take the derivative, you get this. F prime of 2 is undefined. That does not guarantee that it's a critical number, because in this case it's not in the domain of f, so we would not allow that to be a critical number. Anyway, so putting it all together, you can say that if you have a local max or min at x equals c, then you have to have a critical number there. Alright? Alright, so last thing I want to say is this, the closed interval method, which gives us a way to find the absolute max and min of a continuous function on a closed interval AB. It gives us a process for finding it. Remember, we already know that a function has an absolute max and min if it's continuous on a closed interval. How do you find it? Well, you find all the critical numbers like we just talked about, and then all you have to do is find f of the critical numbers, f of the endpoints, and the absolute max and min have to occur at one of those two places. So whichever is the biggest will be the absolute max, whichever is the smallest will be the absolute minimum. Remember this example we looked at earlier? This function is continuous on the closed interval -1 to 4, so where did the absolute maximum end up occurring? It actually, in this particular problem, the absolute maximum ended up occurring at the left endpoint. Where did the absolute minimum end up occurring? Here the absolute minimum occurred in the middle somewhere. Well, if it occurs in the middle somewhere, it has to occur at a local minimum, which has to be a critical number there. So that's how it all fits together. Alright, let's look at a couple examples here. I think we got time. So on your homework tonight, this is the main idea. They give you a function that's continuous on a closed interval, and they want you to find the absolute max and min. Here's what we're going to do. We find the critical numbers, which means you take the derivative, you set it equal to 0. In this case, the only critical number is x equal 2. Then what you do is all you have to do is you find f of the critical number, so f of 2 turns out to be 0. F of the endpoints, and the theorem says one of these three values, the biggest is going to be the max. So the absolute maximum is 4. The smallest will be the absolute minimum. In this case, the smallest is 0. So the absolute minimum occurred at the critical number, and the absolute maximum ended up occurring at the left endpoint. Let's see, I think we got time for one more. Alright, how about f of x equals x minus 2 sine x, which is clearly continuous on 0 to pi. How do you find the absolute max and min? You find the critical numbers, so you take the derivative, set it equal to 0. When you do that, you get cosine x equals 1/2. Since we're talking about 0 to pi, the only value where that's true is when x equals pi over 3. Okay, so now all you have to do is find f of the f of the critical number, f of the endpoints. When you simplify this, you end up getting pi over 3 minus radical 3, which is about -0.07. So the absolute minimum, again, is occurring at the critical number. The absolute minimum would be pi over 3 minus square root of 3, and the absolute maximum occurs at the right endpoint. Alrighty, we'll see you in class.